Porous Media Tea Talk of 2021. I'm Catherine Stern, and I'm joined today with my co-organizers, Maya Rissa from TU Eindhoven, Marcel Nora from Oslo University, and Mohammed Nora also from Oslo University. And our other co-organizers who are joining us in spirit are Kamal Singh from Heriot-Watt University and Tom Boltries and Ariane Massini from Ghent University. So we are back with a bang today with our first session being the Brazilian Interpol special. Both our speakers today are from the Brazilian chapter of Interpol, and we want to extend our thanks to the Brazilian Interpol chapter for selecting today's speakers. And we have a quick reminder before we start our session of Interpol 2021, which will be online this year because of the pandemic, and the abstract submission is now open. So this is a really great thing to get involved with. And the registration for the short courses is also open. So you can follow this link and you can look at them online. Great. So without further ado, we shall begin our talk today. And our first speaker is Paula Reis, who is a PhD student in the Mechanical Engineering Department at PUC Rio. And her research focuses on modeling
Okay, thank you for the introduction, and thank you all for the opportunity to present my work. So today I will talk about the PUC analysis of portability effects on gas condensate flow, which I developed with my advisor, Marcio Carvalho. So what motivated the work were the challenges in production from gas condensate reservoirs. And what I have in particular is that they undergo transition from single-phase to two-phase flow during depletion, which are explained using this phase diagram of the reservoir mixture and this reservoir wearable scheme. So if this arrow over here represents a reservoir isothermal depletion, at high pressures, we are in the single-phase region, meaning that there's only gas flowing from the reservoir to the wellbore. However, at lower pressures, we enter the two-phase region where a condensate dropout takes place. So in the reservoir, far from the well, we still can have the single-phase gas flow, but close to the wellbore, we shift to a two-phase gas condensate flow. And this is an issue because this condensate blocks many of the gas flowing paths and reduces a lot the well productivity in a phenomenon known as condensate blockage. So a possible remediation for this problem would be changing the wettability in this near wellbore region towards a more gas-wet state. This could reduce the liquid accumulation and the blockage of the gas flow. But the problem is that most studies that try to evaluate this method, they perform experiments with either air and water or air and oil as the fluid system, and this is inadequate to represent gas condensate flow. Normally, the phases distributions in the porous medium end up being very different from what they should be, and also the interface potential values are too high. But this is done because it's really complicated to perform experiments with actual gas condensate fluids. The retrograde phenomenon takes place normally at very high pressures and temperatures, and the compositions can be very complex. So as an alternative to experiments, we wanted to develop a pore network model to predict these effects of potability on condensate flow. So to do this, we had to think about how to effectively represent gas condensate flow in such a model. Because while there are numerous models on multi-phase flow, just a few try to represent this fluid system. And the first thing we had in mind is that the phase saturations and properties, they are a function of composition, pressure, and temperature, and they can change a lot during the flow. Just for a simple example, if you have a system at a certain pressure, temperature, and composition, we can split the phases so we can know the phase saturations. Some properties like viscosities and densities also estimate the interfacial tension. And just for instance, by lowering the pressure, we can significantly change all of those properties at once. So to solve this problem, we used a compositional formulation for our pore network model. Then, once we could quantify the amount of each phase and also know the properties, we had to figure it out how they arrange themselves in the porous medium. And this depends a lot on mixability. For a liquid wet porous medium, it has been observed in micromodel experiments the development of a wetting layer upon condensation. meaning that the liquid spreads completely on the pore walls. And then we start seeing this intermittent opening and closing of gas flowing channels with condensate bridges, which is behind the condensate blockage. So a key phenomenon for us to model would be the snap-off of the non-wetting phase. And is my okay. And the snap-off is strongly dependent on geometry. So for this reason, we decided to represent the porous medium as a network of converging, divergent circular capillaries, so that we could use this criterion here for the snap-off. And this criterion takes into consideration this channel length, also the radius of the constriction, the big radius of the extremities, and the thickness of the wetting film. And after doing this, we could finally try to understand the wettability effects on condensation flow. And for this, we looked into the literature of condensation flows in microchannels with different wettabilities. And what we observed is that for liquid wet microchannels, what happens is more or less what I just described. The condensed liquid goes to the walls of the microchannels, and we start having an annular flow of the phases while this configuration is stable. However, for the gas wet channel, something completely different happens. We have what is called a dropwise condensation, meaning that the condensate is collected in droplets, and those droplets, they don't spread. And also at low Reynolds numbers, those droplets they don't move. So they grow until they block completely this microchannel, and then they are advected by the gas, developing a slug flow. So summing up, based on those observations, what we've implemented in our model was for the liquid wet media, we would have the streamwise condensation followed by annular flow. And during the annular flow, the gas flowing velocity is way higher than the liquid flowing velocity, and this leads to condensate buildup. Also, if we meet this criterion here, we have the snap-off of the non-wetting phase. For the gas wet media, we would start with a dropwise condensation followed by slug flow. And in this configuration, both phases, they flow at the same velocity, and we can prevent the liquid accumulation. And finally, in both cases, both gas and wet cases, we can have the capillaries blocked by the liquid. And this happens if we have this condition here, meaning that the pressure drop in a capillary is lower than this value, and this amount of liquid would be equilibrated around the capillary constriction by capillary forces. And with that, we can go to the final part of the presentation, in which I show some results that were obtained with the current state of our model. So those were my modeling inputs. I used a network based on a sandstone with a permeability of 170 millidarcy, porosity was 17%. To represent the different wettability states, we used a contact angle of 0 for the original rock wettability, and contact angles from 45 to 135 to represent the rock after the treatment. This is the composition we used, and it gives us this phase diagram here. Our simulations were at 80 degrees, so we were in this dashed line here, and the pressures I used were between these two arrows, meaning that I had pressure from just below the dew point pressure to pressures in which the maximum liquid dropout takes place. And finally, I tested many different gas flowing velocities to see how they would affect the relative permeability curves. So those are the relative permeability curves we obtained. Here we just have some examples at the lowest gas flowing velocity and at the highest gas flowing velocity. And by looking at them, the first thing we notice is that we have very different ranges of liquid saturation. And this happens because of the condensate buildup in the liquid wet media. Those curves here that were obtained with gas wet networks, we can see that the maximum liquid dropout is around 12%, which coincides with the maximum liquid dropout of our original composition. But here we can see that due to the accumulation of heavier hydrocarbon fractions, we can have condensate saturations up to around 30%, which exceeds our maximum liquid dropout. Also, it's noticeable that the positive effect of flow is more pronounced in the gas wet cases. While those curves here, they do shift a bit upwards, the curves obtained with the gas wet case, they change completely. And this happens because in the gas wet case, virtually all of our capillaries can be blocked by the liquid, while in the liquid wet case, only the capillaries that hold the condensate bridges can be blocked. And the capillaries in annular flow, they do not contribute to this effect. So the effect is less pronounced. And finally, just by looking at those relative permeability curves, it's a bit unclear to quantify the positive or negative effect of this wettability alteration. So to quantify it, we calculated the improvement factor. And this improvement factor is the ratio between the gas relative permeability of the treated and untreated rock using the same boundary conditions, which for our simulations have always been imposed molar flow rate and pressure at the outlet. So once we calculate this, if we have an improvement factor above 1, we have flow improvement, and below 1, flow impairment. And those are the results we have so far. Each of those squares represent one contact angle, so one different level of floatability. In this horizontal axis, in each square, we have pressures from P1 to P6 in ascending order. And in this vertical axis, we have flow rates from Q1 to Q7, representing also in ascending order, representing the gas flowing velocities from 7.5 to 150 meters per day. And by analyzing these results, we can see, as expected, that contact angles close to 90 lead to higher improvement factors because they minimize the capillary pressure. Also, we can see that at lower pressures, we have higher improvement factors. The lower pressures are always in the left side of those squares. And this happens because at lower pressures, we have higher leak saturation and higher interfacial tensions. And those are the most critical conditions for the rock without treatment. So once you treated the rock, the results are better. And finally, just by looking at the gas wet cases, we can see again this more significant rate effect. You can see that from the bottom to the top, we have a more visible color gradient, while here we don't see it that much. And that in the gas wet cases, we could have improvement factors below 1, which means flow impairment. And this happens especially at low gas flowing velocities and higher pressures. And at least those conditions are not the prevailing conditions in the near wellbore region, meaning that even though we use this EOR method, this impairment may not actually happen. So, concluding, with the current state of our model, we could predict that the positive rate effect increased with a wettability alteration, that this EOR method was more effective at higher interfacial tensions, and that at preferentially gas wet media, we could have flow impairment. And this is very interesting because even though we still have a very simplified model, we could see those interesting effects that have been observed experimentally. For future work, I think we have to implement now poles with polygonal cross sections in our model. Also try to figure it out how to implement a more gradual flow pattern transition from liquid wet to gas wet media, and try to include fluid properties on the snap-off criterion. Here we have some references of the works our group recently published in this area. And with that, I conclude my presentation, and I'd be happy to answer any questions you may have.
Thank you very much for the very nice presentation. It's now open for questions. You can type them into the YouTube channel. Yeah, I think it's indicated. Just type in and then we'll read out the questions. And
I have a quick one while people are typing.
Okay.
Can I? So Paula, this the improvement factor is dependent on the phase permeability, right? Could you just mention how you're calculating this phase permeability? How the pressure, is there some pressure averaging procedure that you use to calculate this phase permeability?
Yeah, we have the pressure drop in the network and the flow rate, and we know the absolute permeability. So we use this data and calculate the relative permeability for the gas. I don't know if that was the question.
Okay, so we have already one question in the chat. Nice talk. Kwama Owusu Edoze wants to know if you are to factor in effects of hysteresis, would there be significant changes to your results?
Well, I assume by hysteresis he meant contact angle hysteresis. And if that's the case, I think that, yeah, they would affect our results. I mean, since this was our first model, I tried to make it as simple as possible. There are many things we can do regarding the contact angles. Maybe instead of using just one value, use like a distribution of values, and also implementing the contact angle hysteresis. I think that it would definitely change the results.
Thanks. And there's one more from Said Zadeh Najat. Thank you very much for the nice presentation. Do you use the compressible model for the gas flow?
Yeah, we have a compositional model. So depending on the pressure, I mean, the densities and the actually, I had a slide here. I think that may help answer this. But our here, our model is compositional. So one of the equations we solve is a volume consistency equation. So we have to match the volume of the phases with the volume of the pores, and those volumes change a lot with pressure. So yeah, we take this into consideration.
Okay. And here's one more by SM Hosseini Nasab. How well perm in slide number 10 are made with different angles?
Let me go back to slide 10. Yeah, so yeah, those, I think he meant like those angles here. And we just run the simulation many times. And for instance, like this pink curve was obtained by using the contact angle of 75 in the whole network. And then we run the simulations all over again with 60 and 45 and 0. Each of those curves are obtained using the same contact angle in the whole network. And then we run the simulations many, many times.
Have you considered also looking into mixed bed systems?
Yes, yes. I think that it is also would change a lot of our results. One thing I wanted to do, maybe it's a bit complicated, but is to first simulate the injection of these chemicals that change the wettability. So maybe they overpass some parts of our network. So we would have just like, guess what, pores in this path of this chemical, and then liquid wet pores in the parts that it didn't go. So yeah, that would be very interesting. It just didn't do it yet.
May I also ask how long, what is the time scale of the alteration process?
Yeah, that depends a lot on, for instance, in this case, we simulated a composition with 7 components. So yeah, that makes it a bit slow. And it depends on the size of the network. This one was not very big. And also one thing that makes the simulation time change a lot is the thermodynamic condition. When we are just below the dew point pressure, sometimes it takes a long time to reach the steady state conditions. And at pressures that are like further down, like not too far, not too close to the dew point pressure, we reach the steady state faster. I mean, it depends on, there are too many variables, it depends a lot.
Okay, I see. There is one more question here by the audience, by Ahmad H. Zadajan. How did you model phase change in the PNM?
Yeah, I think it's again that slide here. Maybe I should have included it. So our composition formulation was based on the work by Collins in 92. And in this formulation, we have our main system of equations with a transport equation, which we use here, the molar balance equation, and the volume consistency equation. And in this formulation, the phase equilibrium calculations, they are decoupled from this main system. So we solved this system of nonlinear equations with the Newton-Raphson method. And at each Newton iteration, we perform the phase equilibrium calculations. So this is how we have the phase change in the model.
Okay, great. Well, these are all the questions which were in the chat right now. So I would like to thank you very much for the great presentation. And with that, I would like to move to the next speaker, which is Maedo from Sao Paulo State University in Brazil. And he's going to present on modeling heat and fluid mass transfer through induced fractures in deformable porous media. So with this, I would like to give a stage to Michael.
So thank you all for being here today. Also, many thanks to the Interpor for the invitation. As the chair mentioned, I'm Michael Maedo, postdoctoral researcher at São Paulo State University. And today I'm going to talk about modeling the heat and mass fluid transfer through induced porous media, through induced fractures in deformed porous media by using a very simple technique that can be implemented in any existing finite element code. But before I go through this, I'd like to thank my colleagues that have been working with me over the years. Dr. Manzoli, Dr. Bittencourt Jr., and also Dr. Rodriguez, who are experts in structural engineering. I also would like to thank Dr. Sanchez, Dr. Guimarães, and also Dr. Cleto, who are specialists in geotechnical engineering. So let's start by asking ourselves why it's important to model the fracture behavior or to understand the fracture behavior in porous medium. Well, in petroleum engineering, for example, it is important to induce fractures by injecting a fluid at a very high pressure to increase the permeability of the medium, and therefore to facilitate the oil and gas recovery process. This method is called hydraulic fracture and may involve a thermo-hydromechanical process to take into account the main phenomena related to the process. In the case of the enhanced geothermal system, cold water is pumped down in a well to induce hydraulic and also thermal fractures, and hot water and steam is recovered from a production well. So this hot steam and hot water is usually used to produce energy. Well, but generally, finite element programs are able to model heat and fluid mass transfer only in continuous porous materials. We're not capable of capturing this continuous caused by the fractures. So, in our case, for example, we have used the finite element program CodeBright to take the fracture formation, but the code was originally designed to handle only continuous porous media. In this case, the coordinate equations used to describe the behavior are given by the balance equations. Here we have the mass balance equations of water and air, also the internal energy equation. In this case, we also consider that we have thermodynamic equilibrium between the solid and liquid phase. We are not considering the air mass balance equation, so there is only one phase. And also we consider as the balance equation, the moment balance equation. So we have here all the balance equations for the continuous media, and also we need the constitutive laws, constitutive equations that relates to variables. In Fourier's law, for example, we're gonna relate the conductive heat flux with the temperature gradient. But this formulation that I presented before, it's only able to model the continuous behavior of the fracture, the porous medium. It's not going to be able to tackle the fracture formation. So we use this very simple technique called mesh fragmentation technique, in which we inserted high aspect ratio interface elements between the regular lens elements of the mesh. So these are the main steps that we need to go through before the analysis starts. So during the pre-process stage, we created a mesh in Gmesh, GID, or other software. Then let's suppose that we have two materials. In one of them, we're going to reduce the size of the material, of the elements. And then we're going to start in this void high aspect ratio interface elements. These elements is the traditional three-node triangular elements, the case of 2D, that you can find in any finite element code. So you don't need to implement a new finite element. In the case of 3D, you can use the four-node tetrahedral elements, but we are not going to show any 3D study here, only 2D for this moment. And this technique is very easy to implement because we don't need to create anything new. The only thing that we need to create is the damage model and also the constitutive models related to the degradation process. So we implemented this tensile damage model. It's very simple. The details can be found in our paper that we published in 2016. Before the stress overcomes the tensile strength in our model, these high aspect ratio interface elements are going to ensure the continuity of the displacement and also stress field. When we consider also the hydraulic and thermal behavior, he's also going to make sure that the temperature and also pore pressure field are continued. Okay, he's going to ensure the continuity of the variable fields. So once the stress overcomes the tensile strength of the material, the degradation process starts, and then the behavior is going to, the behavior of the material of the high aspect ratio element is going to exhibit the behavior of a fracture. So we also need to enhance the intrinsic permeability by using the well-known cubic law. And also in the Fourier's law, we need to consider only the thermal conductivity of the liquid, because once the fracture opens, the fracture is going to be filled only by the fluid. There's no solid phase there. We also need to enhance the permeability according to this law. And that's all we need to do to use this technique to model the fracture behavior. That's why it's so easy to implement. You can do it in any existing finite code because you usually have access to the material library. We don't have access sometimes to create new elements, but to create new material constitutive laws, we have it. And to validate our case, first, to validate the hydromechanical behavior of fractures, we use the KGD model. We consider the plane strain deformable porous medium. This case was proposed by Garrier and Granet. It has also analytical solution. In their work, they consider zero thickness interface elements. In our case, we are using high aspect ratio interface elements that are inserted in this line here only. We also consider a far field stress at the top and at the bottom. And then we're going to inject a fluid at very high pressure to induce the hydraulic fraction that's going to develop in the central part here. These are material properties of our case. And then we compare our results in terms of fracture aperture, liquid displacement, also fracture length and injection pressure with the ones obtained by Carrier and Granet, and also with the analytical solution. We consider K here is the intrinsic probability, and it's possible to observe that this technique that we are proposing it was able to capture the main trends associated with the hydraulic fracturing phenomenon when we compare our results with the analytical solution and also the Carrier and Granet work. And also, so this case is only considered the hydromechanical behavior, but we also know if this technique is also able to tackle the thermal behavior of the fracture. So we consider this laboratory experiment conducted by Dr. Cha in 2016, in which you have a transparent acrylic sample, and you have a hole in the middle. He put two steel tubes. In one of these steel tubes, he's going to pump down liquid nitrogen at very low temperature, close to 200 degrees. And in the other tube, he's going to pump it up, this liquid, because he wants to keep the flow rate constant. He doesn't want to induce any kind of hydraulic fracturing. He wants to analyze only the fractures induced by the thermal shock. And then we created an axisymmetric model with this mesh. We also insert high aspect ratio interface elements between all of them. And then we compare the evolution of the fracture pattern that we obtain with our model with the ones reported by Dr. Cha. And we also here is the evolution of the temperature in our model. It's possible also to observe that the fracture pattern is our model is capable of capturing the main trends associated with the crack pattern observed in the experimental results. This is the last case, a thermohydromechanical analysis. Is a very simple case. We're still under investigation. We are trying to analyze, to understand better. The behavior is a 10 by 10 meter porous medium. The initial temperature is 70 degrees Celsius, and the pore pressure was initially set to 10 megapascal. We also have a 20 megapascal applied at the top and 25 megapascal applied at the right face. So we want to induce anisotropic stress state, and then we inject water at 0.01 kilograms per second at a temperature of 20 degrees Celsius. So the fluid here is, the temperature of the fluid is much lower than the temperature of the initial reservoir. This is the fracture pattern that developed due to this analysis. So first, we conduct this numerical analysis in 2 stages. In the first stage, we induce the hydraulic fracturing by injecting a fluid here, and then it's going to develop only in the horizontal direction due to the stress state. The horizontal stresses are much higher than the vertical stresses. And then in a second stage, we're going to consider 2 points here and here, in which we are going to extract the fluid. Why we are going to do this? Just to keep the flow rate constant, as well to induce the thermal cracks. The thermal cracks is going to occur mainly because of the shrinkage behavior of the medium when it has contact with the fluid at lower temperature. And this is the pressure and temperature field evolution throughout 10 hours of injection. As you can see, there is also the secondary cracks emerging from the main hydraulic fracture. So as a conclusion, I would like to mention that this technique that is very simple to implement in any finite element code is able to study the thermohydromechanical behavior of fractures in porous media. We are still not considering phase changes. And also, we don't need to implement, with this technique, you don't need to create new kind of elements in your code. You also only need to implement new constitutive laws. So that's why it's so attractive. And the fracture is going to develop only due to the stress state of the body. And also here are some references, some publications that we have been working on in the last couple of years that we have published. And these are contact information if you guys have any questions after also the interpore. And that's it. Thank you, guys.
Thank you, Michael. So we move on now to the second round of questions. So if anyone has a question, please type it in on the comments. And also if the studio has questions, please feel free to ask. I have a quick one in the meantime. So you mentioned the comparison with the analytical model. Could you just elaborate a little bit on that? Is it a linear mechanical fracturing model, or you go to the non-linear one? The analytical one, I mean.
The analytical one is non-linear, the behavior of the fracture, but there's several simplifications in this model. One of them is, can I go back just to explain something really quick?
Sure.
So one of the things that when we compare with the analytical one is that the injection pressure that we obtain with a model is higher usually than the analytical one. Why is that? It's because of the backstress effect. This backstress effect is due to the coupling between the hydromechanical behavior, because when you have the fluid penetrating also in the porous medium, it's going to affect the stress state of the body. And the analytical solution does not consider this. And between all the analytical solutions that we have several different solutions because it depends on the permeability and also the viscosity of the fracture. And in this case here, we compared with the called near K solution, in which you have smaller permeability, but also the viscosity of the fluid is very low. But we have also more other analytical solutions. Some, they have different names that depends on the behavior of the fluid and also of the fracture. Because if the viscosity of the fluid is high, you also need to take this into consideration of the fracture aperture.
Right. Super. Thanks a lot. Do we have any extra questions? I think we have one here. So Yu Chen, thank you very much for the great presentation, Dr. Maedo. Quick question. Any suggestion on how we can determine the tensile strength of the soil material?
Well, the soil material is a little bit harder because usually in soils, we need to compress. The soils are usually under compressive stresses. But there is a very simple test in which you model, you create your soil sample, is a cylindrical one, not a cylindrical one. Usually a cylindrical one for the triaxial, but they have this very simple, the shape is this kind of, I don't know how to explain, but you have a large part in which you're gonna put two equipment, you're gonna pull out your soil, and then you're gonna measure the evolution of the tensile strength of the soil. But in this case of the soil, the tensile strengths are very small compared to the rocks, of course, because we are conducting numerical models with numerical experiments with rocks, so the tensile strengths are much larger, and in soil, usually the tensile strength is much lower. But we have some equipments that are able to do this, and we have some paper. Dr. Manzoli and Dr. Sanchez, Dr. Guimarães published a paper actually showing a photo of this kind of equipment that I can show you after the presentation, of course.
Great. We have another question here from Gabriel Varela. Great talk, Michael, and very interesting results. Could you comment on the computational cost of your model, say compared to phase fields, for example?
Yeah, so there's the only problem with our model, I'm not gonna say that's a problem, but it's a fact, it's that we increase the degrees of freedom because, well, as you can see here in this figure, when you insert the high aspect ratio interface elements between the regular elements of the mesh, of course, you're going to increase the degrees of freedom in your case here. So that's one of the drawbacks that we still are trying to figure out how to overcome, especially for 3D cases. Because in 3D cases, of course, it's a thermohydromechanical, you're gonna have 6 degrees of freedom, 6 extra degrees of freedom per node. So this is one of the drawbacks. As advantage, I would say that all the implementations are pretty straightforward in my opinion. You have usually access, like I said, to the material library, but in terms of computational cost, it's true that sometimes if you don't have any kind of, sometimes you also can implement some new techniques. So instead of insert the high aspect ratio interface element before the analysis, you can introduce during the analysis. But of course, there is also an additional cost because you're gonna need to check if the stresses are very close to the tensile strength of the material, and when it is, for example, 90% close, you're going to insert this high aspect ratio interface element, but also has some cost. So it's great. You're going to have time to study this kind of behavior. It's pretty easy to implement, but it's a drawback that it still needs to overcome because it's true that we increase the degrees of freedom in the final element mesh.
Super. Thanks, Michael. I think that closes our questions and that closes this session. So I would like to thank you once again. And
thank you, guys.
I would like to, yes, thank you both to you and Paula. And together with the rest of the team, I would like to express my gratitude to the Brazilian Interport chapter who has helped us in this journey here to start this section of Interport chapter special. So thank you very much. It's very, very nice that you helped us organize along the way. Of course, being Brazilian myself, I'm extra happy with the results, so I have to say it. And I would like to take the chance to announce our next session, which is coming. Let's see if I managed to put it on the screen. There it is. Okay, so it's on the 9th of February, so 2 weeks from now, at 10:30 Central European Time, and we're going to have two talks one by Senyu An from the University of Manchester on the effects of pore size correlation lengths on two-phase flow and transport properties, and also another one by Oshri Borgman from the Université de Henan, and it's on the impact of matrix deformation on drying of granular materials. So I think that closes the session. I would like to thank you all once again. The Porous Media Tea Time Talks team, you see it on your screen, and we hope to see you again 2 weeks from now. Bye-bye.